I'm happy to be at ICTS and thanks for inviting me. So today, so my name is Navin Chaurasiya. I'm a PhD student at IUCA and I work with Professor Surud Murray. And today I'll be talking about my project on Galaxy Hello Connections. So yeah, so let's see. So the question, right. So the question that we ask is, so first of all, I would like to just make a connection with whatever we have been hearing here and learning. So we have been talking about modeling the understanding the particle nature of the dark matter halos or different things, dark energy, and understanding or modifying cosmology to get consistent explanations for many probes and so on. But among all these tensions, there is one more element of understanding the astrophysics of galaxies and their connection with dark matter halos, which is a piece in the puzzle also. And so my talk is in respect of that. So the thing is, we know that the halos are dark matter halos are biased with respect to the matter distribution, and the galaxies reside inside the dark matter halos. So that is the reason why we use galaxies as traces of dark matter halos. So the one question is, how do galaxies populate these dark matter halos as a function of redshift and as a function of the properties of the galaxies itself? So this question, once we understand, we'll be able to better understand the it will be a help in understanding the how the galaxy properties and halo properties they evolve, and what kind of scatter is there in the astrophysics of this relation. So so like one of the results this is a key result that I am interested in. So the stellar mass halo mass relation, this is a plot from Banerjee et al. To 2010, and there are more recent results also, but difference is not too much. So I'm just going with this one. So you will see that as you go on the vertical axis, stellar mass increases, but you also have to look at the slope of this curve. So slope is little bit higher compared to the high mass end. So you say that, okay, specific star formation rate is higher, and on the other axis, you will see that the halos, dark matter halos are accreting more and more dark matter and becoming heavier. So that is the other axis. And the ratio is kind of the efficiency of star formation kind of thing. And this encodes the understanding how at what mass galaxies are more efficient in building up baryonic mass, and how are their dark matter halos growing at the same time. So so this is the question that I'm interested in, and so these are the abundance matching constraints, and we will be using weak lensing as a direct probe of masses, because in abundance matching and you infer the relation, there are assumptions involved. One of the key features of key aspect of lensing is that you measure the dark matter total matter directly, right? So so I'll just quickly try to go with the basics of the lensing for if there are students who don't work in this field. So you have to look at this between the planes here. So this is the observer here. There is some background thing. So let's think that this is some galaxies distributed at some redshift. So these are we call them as lenses. So there will be some background galaxies behind them. So the thing is, if you just look at them, this is the observed plane, right? So I'm just showing you what happens if there is no weak lensing. So what will happen is these yellow things are the galaxies, lens galaxies, and they are also randomly distributed according to each other. If there is some and the white galaxies are like these background galaxies, and these background galaxies, their shapes are also randomly oriented with respect to these lenses. But in observed plane, what happens is you don't see that kind of thing. What you will see is the shapes of the background galaxies will have some tangential component induced because of the lensing. So you will see that these white things will have slightly tangentially oriented. This is an exaggerated picture, but just to give an idea. Now, the weak lensing signal that we measure here as a function of radius, it has like two components broadly. One is the shear, tangential shear, average tangential shear, because we will be stacking over a lot of lens source pairs. So this average is for that. And there is another component which is the geometry, which relates the geometry of the distances between observer, lens, and source. Okay. So so what kind of data we use and how do we measure it, right? So that is one thing that I want to quickly tell you. So in HSC, we use this wide layer galaxies where the number of galaxies are pretty high. I'll be talking about these through two redshift in Z1 and Z2. So Z1 is like 0.3 to 0.55, Z2 is 0.5 to 0.80. these galaxies, so we'll be binning these galaxies as a function of stellar mass thresholds. You will see on the x-axis is the stellar mass. So all the galaxies greater than 8.6, those numbers are like 10 to the power 6, something like that, and so on. So this is the number distribution, just for quick understanding. So we'll be using some 6 fields in the HSC, and the photometry that we'll be using is photometric data. So the stellar masses and redshifts are derived from a Mizuki catalog that we'll be using here. And the total area that we'll be concerned with is 126 square degree roughly. And also because our lenses and sources fall in the same data, so there will be full overlap. Why this full overlap is important, I'll tell you shortly. So these are my binning schemes, stellar mass thresholds and redshifts. Okay, so how do we measure these signals? So first, so what we have to do is you have to realize that this is measured at different radii. What is this radii? It's a projected radial distance. So what you need to do is you need to count the pairs of lens galaxies and source galaxies in the background. Lenses are foreground, source galaxies are background. So you count at a given separation how many pairs are there, right? So more the pair, better the statistics, and better will be your signal to noise ratio. So the key thing in weak lensing analysis is that if you have more and more area, that's why then you will have more and more lens and more and more lenses. And if the overlap is better with the background galaxies, you will have more and more sources. So the lens source pair will increase in count, and the errors will go roughly as square root of n. So more the number, and you will get better signal to noise ratio. So, and secondly, the geometric factor has this form roughly, exactly actually. So it has distance to source, lens, and between them. And I just want to point out the feature of this function is that when the lens and source are very close by, this function peaks very sharply. Otherwise, it falls off very quickly. So that is one feature. I will. So this is useful when we average it. Okay. So I'll just let me just go. So I'll tell you. Okay. So yeah. Okay. So while averaging, we also weight it by some weights based on the lens source quality, based on the quality of the shear that you have measured, quality of the tangential shear that you have measured, and various aspects. So this sigma crit is used as a weight, and I will show you what combination we use there, which is sensible. So there are issues in how you separate sources from lenses. So there are some things that we use to tackle this thing. So one is separation of sources versus lenses population with if we use full PDF, because we don't have the spectroscopic redshift, so we use only the photometric redshift, right? But we have a PDF of this redshift. So what we say is, we say that if there is some redshift, maximum redshift of your lens, then ZDiff is like 0.1 for us. So you say that if the overlap of the source redshift PDF is greater than 99%, plus some factor here, only then you take it as a source. Otherwise, you just skip it, because there is a high chance that it could be a lens, a galaxy related to the lens distribution. So these kind of contaminants, if you don't remove, they contribute to your lensing signal and they dilute the lensing signal, and then your interpretations will be off. Okay, and see, the other thing is using full ZPDF while stacking the excess surface density. ESD signal is basically excess surface density signal, which is nothing but the lensing signal, to avoid contamination again. So yeah, so this sigma crit inverse, like I told you, sigma crit has peaks very sharply when the lens source are very close by. So inverse of it is it will be very low when the lens source galaxies are very close by, and far off when they are far off, it will be high. So this weight kind of gives more weightage to galaxies which are separated, lens source pair which is separated largely. Otherwise, it downweights other things. This also helps in kind of curbing the contamination. Okay, so this is the full equation that we use for lensing measurement, and there are many data related things, factors, some multiplicative bias, some additive bias, but overall the understanding is the same. This ET is the tangential component of ellipticity that you measure, how much tangential shear has happened, and then this is the kind of weighting thing. This WLS is the weight for this stacking, averaging, and this weight is the minimum bias estimator kind of thing, right? So now once you know what is the weak lensing signal, how you measure it, I have not talked about the factors, multiplicative and additive biases because of lack of time. So I'll just go ahead. So signal measurement in, okay. So let me just skip it. So these are all just related to systematics, and we have checked that the systematics are within bounds. Okay. So I'll just try to show you what are my results. So once you measure the signal, then you also have to model it to infer some halo masses and other properties of your galaxy distribution. So in the modeling, there are central and satellite functions that halo occupation distribution functions, which are used to fill up the halos of certain mass with galaxies. So I'll also skip. I'll just mention that there are 5 parameters. This log m min is the mass of the central halo, and this is the scatter in the central halo. And I'm more interested in these 2 parameters than the satellite parameters, so I'll go ahead with it. And so there are some priors in this modeling. So we use a Bayesian analysis, and where the priors are mostly the flat and wide priors, just to keep it uninformative. Right, and these are just the constituents of my modeling, so I'll skip it too. I just want to show you the results. So these are the fittings. Now the key feature is that the signal to noise ratio in observation is like 50 and above, which is very nice. So this gives us good constraints on the fitting. Now clearly the modeling succeeds in fitting the signal, and yeah, and this blue, I just want to show you the blue signal. Blue signal is a result from HOD modeling of abundance and clustering using the same data that we have used. And clustering data doesn't reproduce a lensing signal. So what we are doing, we are using abundance and weak lensing to fit the signal, and then see what are the stellar mass halo mass relations compared to the clustering analysis. Okay, so this is in another redshift bin, and again the fitting is very good, just that the signal to noise ratio is a little bit lower because number statistics goes a little bit down. So how are the constraints looking? So the stellar mass halo mass relation that I talked about, this is a parameter in the modeling. Okay, just to heads up, this min parameter is not the best constraint by the weak lensing. Best constraint parameter is the average halo mass, which I'll show you next. But this is a relation which has been compared in literature, so I'm showing you. So this is the 1 sigma and 2 sigma error bands in my analysis, and the clustering analysis is here, this red point with error bars, Ishikawa. What you will see is at the lower mass end, they are kind of consistent at slightly at the lower halo mass end, but at the high stellar mass end, lensing predicts little bit higher mass. However, as I go to higher redshift bins, they become more and more consistent. This could be the reason could be that at high mass, at high redshifts, here the HSC's median redshift is close to this redshift. So that means HSC will have better photometry and better modeling of galaxies. So probably redshift and stellar masses will be better here. So there are components to understanding this plot. Okay, there will be errors in the stellar mass. So a stellar mass is for us is just a label. It just tells me from a catalog I have a stellar mass, and halo masses are my inferred values. So this understanding, this is also a task which we are currently doing right now. Yeah, it's not changing, huh? Right. Just, yeah. So I'll just quickly tell you that once you use abundance, so the errors in abundance have consequences on your understanding. So if I just so you see that this orange one is little bit higher abundance than the blue one. Blue abundance is coming from the clustering analysis that I'm comparing with. So those are here. So because lower abundances will use slightly higher halo masses here. If I take higher higher abundances, this will go down a little bit, but it also have its consequences on the sigma log m, right? So keeping that in mind, so if I were to believe that what are the constraints on stellar mass halo mass relation using the abundance from I20, that is the one clustering analysis, and this is some Muzin et al. 2013 analysis. So what you will see is that the trends in the stellar mass halo mass relation here, if Z1 is at high mass end, if Z1 is giving you higher halo masses, then that has potential to change with the information of abundance. Similarly, the abundance is also controlling also your this sigma log m. So this inference has to be kept in mind. But at the same time, the best constraint thing here is the stellar mass halo mass relation. The average halo mass relation as a function of the stellar mass. So what you will see, the error bars are much smaller, and this is kind of trend. I would just mention it in the results section in my conclusions. And just this is the last plot which shows you what happens if I only use weak lensing and if I don't use abundances compared to if I use abundances. So these hatched regions are with the weak lensing only. So it clearly shows you that the fitting is not completely dominant, or it is not dominated by abundance. It is weak lensing is setting the bar for the halo masses, and abundance, inclusion of abundance kind of brings it a little bit down. So this is just one abundance from the clustering analysis. If I include other abundance, so you will have slightly here and there. So I'm not including that plot here because of maintain clarity. Satellite fractions, there are features. It's just that satellite fractions go down as you go to higher central mass, stellar masses. It is hard to comment on satellite fractions trends by using either only abundance, or by either using only weak lensing or both of them. So I won't comment on this right now. So these are some of the results, and yeah, if there are some questions, I'll show you some other plots. Thank you.
Okay, time for one small question while the next speaker sets up. Anyone question?
So why do you, I don't think I quite follow why the differences between the previously measured min as a function of halo mass is worse at higher masses. Do you understand why?
Right, you mean?
At like higher halo mass.
At higher halo masses?
Higher stellar masses.
Mm-hmm. Why this? So this is redshift bin 1 and redshift bin 2.
Yeah.
What you are asking is why they evolve in redshift.
Yeah, particularly at higher stellar mass.
I'm trying to compile all these understandings. Okay. I don't have a very clear idea of it. So yeah, let me think for a second, or maybe I will.
So we can chat.
Yeah.
Later also. Yeah, because you said that it might be because the HSC redshifts are better higher at higher redshift. That's the median redshift of the HSC survey.
Well, when I said that I said that as a possibility, because why previous studies are matching better. I'm not biased to previous studies, but I'm just saying that could be a possibility, because it is true that photometry becomes better at median redshift of the HSC. That is true. And there are error bars on the x-axis. So this has potential to shift on the x-axis also. So that is also a critical point actually. So this understanding is, I'm trying to understand by using simulations and try to see if I take true if I take true stellar masses in simulations and if I give it some scatter, what happens? What I have clearly seen is that including scatter in, let's say this is the true, these are the true stellar masses. Okay, let me clearly tell it. If I take all the some galaxies in some redshift bin and in some threshold stellar mass, okay, and then I perturb the redshift of these galaxies by some scatter, realistic scatter. I got that by comparing with Cosmos data. And then what I do is, then I can also perturb the stellar masses of these galaxies, just because the mass to light ratio will shift if I move it up and down in the redshift. So what happens then? I bin those galaxies in observed redshifts and observed stellar masses. So this is, let's say if this is my stellar mass limit, like 8.8 or something, maybe 8.6, then in true plane, if you see, what you will find is it is slightly heavier. It's not really the lower threshold. So that means all those plots that I showed you, it could potentially shift on the x-axis towards maybe agreement with the previous studies, but still it will have a large error bar. So the point of this study is that you can do such kind of analysis by using photometry, better photometric data. As future surveys will come, this thing can improve. And not only that, there is some more potential in it. If I combine some other probes, if I combine some other probe like clustering or something, then this can improve. Also, if I take joint fitting, then again it can improve because of the covariances across planes. So modeling of covariances can become better.
Okay, let's thank the speaker again. And